So, welcome back, everybody, and I hope you had a good break. So, what I wanted to do now is to give you the kind of paths which we can follow for the second project. And obviously, as you saw from the email, there is also the possibility that you define something which you find more interesting than what I'm going to propose. And I don't get offended if you don't like what I propose, okay? So, how I will focus the lectures in the coming weeks, the coming 3 to 4 weeks, is actually to focus on solving the problems we had or similar problems in project 1 with machine learning methods. And I want to use today to explain to you the basic approaches which we are going to follow. And one is based on a set of methods which in machine learning are called generative methods. And there is the reason why I bring up these generative methods like Boltzmann machines. And for people with a background in the physical sciences, Boltzmann machines are pretty known. This was introduced by Giuseppe Carleo in 2017, together with Toyer. And there's a paper which is very much cited where they actually use Boltzmann machines to solve quantum mechanical problems like those which we had in project 1. So that gave actually that sparked the whole field of deep learning and many-body physics. So I would like to focus on that because when you are going to see what needs to be programmed, you can recycle most of the ingredients which you developed in project 1. So the way you calculate the gradients, the integrals which are involved, etc., they are the same which you can then reuse when you set up a Boltzmann machine, which in essence means that you replace the trial wave function with either a neural network or a Boltzmann machine. So that's a kind of overarching view, the bird's view on the topics which I will discuss in the next 3 weeks. So with that material, you can actually easily recycle everything you did in project number 1. So that's one of the paths which we will have for project 2. And as you see here, that the material which you see here obviously depends on your interests, what you want to do. And the material here on Boltzmann machines, we will continue the discussion next week, and we will also discuss about neural networks. Now, if we now look at the alternatives for project 2, there's one alternative, which is you taking project 1 and replace bosons with fermions. And then what you would need to do is to bake in the anti-symmetry of the wave function with a so-called Slater determinant, which then gives you the anti-symmetry, because these are fermions. And for those of you interested in that, you can see that also as a continuation of project 1. The only thing you need to do is to bake in the anti-symmetric ansatz for the wave function, which means that the single particle piece, which previously was just a product of harmonic oscillators, now needs to be a determinant. That's the way you bake in the anti-symmetry. Your Jastrow factor, the correlation part, is symmetric. So you have a symmetric times an anti-symmetric function, which becomes anti-symmetric. So that would be what we call fermion variational Monte Carlo. So if somebody's interested in that, that is a very, I shouldn't say straightforward, because you have to bake in the Slater determinant, as we call it. It's a determinant. And for those of you familiar with many-body physics, these are pretty known concepts. So some of these projects actually favor those of you who have taken a course in many-body physics. Then the topic, so the fermion variational Monte Carlo, I have a set of slides. So what I'm going to do that, if you opt for that, is that we can have more separate discussions, because I will not be able to cover everything in the lectures. So in the lectures, I will actually focus on point 2 here, which is deep learning apply to project one. And you can then see what you want to do, whether you want to stay with just Boltzmann machines. And you will see then for a specific type of Boltzmann machine, a specific ansatz, you will actually get exact results for the harmonic oscillator wave functions. But as soon as you bake in interactions, you will see that this actually doesn't give you good results. On the other hand, with a neural network, you will actually be almost spot on perfect results. So it depends a little bit on how much time you have and how fast it goes. So the Boltzmann machines, if you don't have any, how to say, obstacles in implementing it, is something which can easily be implemented with your program by just changing the trial wave function and just keep what you have. And I will show you later today how this comes through. So the Boltzmann machines can be implemented in short time, 2 to 4 weeks at most. And then if you have time, you could start looking at neural networks. Alternatively, you can jump into neural networks immediately if you have familiarity with that. Then we have 2 proposals which are more tailored to what we would call the many-body physics aficionados. And there are some of you who are interested in Hartree-Fock theory and time-dependent theories. And there is a project there which I'm going to link to. And then some of you have also studied many-body methods like coupled cluster theory. And there's a project tailored to those of you who may be interested in that path. Then there are obviously suggestions from you. So I hope this doesn't give too much confusion and that there are enough things that you can look at and then make your judgment and make your decision and see which one you want to look at. And we can discuss many of these things after the lecture today when we discuss the project work. So the projects, I've actually placed only 3 of them now. If you go to the website of the course, you will see that there is a coupled cluster part. This is just a Jupyter notebook. Just take a look at that one. The PDF contains a LaTeX file. There's a machine learning project. I may actually make some changes to these projects. And there is a time-dependent Hartree-Fock project. And I know that the 2 of you may be interested in doing that. So you don't need to make your decisions today, but we can keep discussing this during the lab session. So today's lab sessions, I mean, is more getting started with thinking about project 2 and what you would like to do, okay? So what I wanted to say a little bit about now is the basics of some of these machine learning methods. So there is a paper, I'm going to actually link up that paper. So there's a paper after Giuseppe Carleo, and let me just bring it up. So if you just plug in Carleo and Troyer, you will find this paper here, which is a science paper. I dislike this. Okay, so this scientific article here from 2017 has really sparked off the studies of deep learning methods coupled with the quantum mechanical many-body systems. Now, I should also say another thing. So this is a small digression when it comes to these type of systems. In the project, which I have, I propose a harmonic oscillator lookalike problem. So that means that you could take what you did in project 1 with a non-interacting case and replace the trial wave function with what we are going to call a Boltzmann machine later today. What these people did was, however, to use other types of Hamiltonians. In solid state physics in particular, there are some highly popular quantum mechanical Hamiltonians, which are based on the interactions between spins. And some of you have encountered models like the Ising model. That ring a bell? There's a quantum mechanical variant of that. We have the Heisenberg model. Maybe you've heard of that as well. There is the Anderson model. There is the Potts model, etc., etc. So these are type of models where you just have interacting spins located on lattice sites, and then you have a constant interaction strain. So in this article, they actually studied the quantum mechanical Ising model using Boltzmann machines. And you will see why the quantum mechanical Ising model is a kind of lookalike of a Boltzmann machine trial wave function. Okay? So this is one paper which can serve as a kind of motivation. And after that, I should say there are hundreds of papers every year which deal with new refinements on using deep learning methods to solve quantum mechanical manipulation problems. So I am one of the people who actually do that. And I should say that the degree of precision is amazing. You basically beat with very few efforts the best benchmark many-body methods, which is diffusion Monte Carlo, which in principle gives you the exact ground states, if you can simulate long enough. So the nice thing with a neural network and why these are so popular is, one, you can use the variational Monte Carlo machinery if you want to. So there is no problem. So when you do a diffusion Monte Carlo calculation, the way you use that is that you have your variational Monte Carlo result as an input to the trial wave function. But then a diffusion Monte Carlo is you rotating time into imaginary time. And if you let time evolve, this imaginary time evolve long enough, you can actually show mathematically that you should reach the exact ground state. But you need to feed in an ansatz for the wave function with the ground state energy from a variational Monte Carlo problem. Now, a diffusion Monte Carlo problem is actually you translating Schrödinger's equation into imaginary time, and then it becomes a diffusion-like equation. The problem then with a diffusion-like problem is that your wave function is now the probability distribution, the wave function itself, and it's given by the distribution of random walkers. Now, when you have an antisymmetric wave function, your wave function changes sign when you flip positions. A probability distribution of random walkers cannot be negative. It doesn't make sense to have a negative probability distribution. And that leads to a famous problem, which is called the Monte Carlo sign problem for fermions. And I have, this is a problem which people have dealt with for ages in many body physics. And I would say it's at the level of, if you can solve that properly, there is a party in Sweden which you can go to in December. I think you even meet the Swedish king and you get a prize and some money. I think the problem is at that level. When you do neural networks, on the other hand, you can keep the variational Monte Carlo machinery. And your trial wave function is the neural network, or this Boltzmann machine, which is another neural network. And with that, you can start simulating. And that gives you an immense flexibility, because the neural network is agnostic to almost the type of system which you have. Whereas when you solve problems with different many-body methods, you need to mount a huge mathematical machinery to solve a problem. And those of you who have taken many-body physics, you know that. If you deal with differential equations, you go from 1 to 2 dimensions, you may have to change method, etc., etc. So these deep learning methods have actually offered the whole community of people who do many-body physics a huge step forward. But this is the kind of propaganda from my side, okay? But it's actually fun because many of you have taken a course on machine learning and you know the basics, and you will see that it actually gives you an interesting flexibility in study many-body systems. So I wanted to say a little bit about these Boltzmann machines and also obviously neural networks. So what I'm going to do now is to switch a little bit to the whiteboard, if that's okay. And I want to spell out the basic details which you would have to deal with when you're going to study deep learning methods applied to quantum mechanical problems. So Boltzmann machines belong to the type of methods which are called generative methods. So what you do then with your data is that you generate a probability distribution. This is a generative method. And when you have a probability distribution, what happens then is that you can, one, obviously generate new data. With a probability distribution, you can have a proper estimate of the standard deviation because you have a probability distribution. Two, you have a, let me just switch off this sound here. Just do that one and just switch off. Okay. The generative methods then, what you do then is that you generate both a probability distribution. The probability distribution allows you to make prediction, to generate new data, and you can estimate the standard deviation from the probability distribution. And you can also study correlations, and you can study causality. So what is the likelihood of A given B? Now, when we have used a standard neural network, which is often called a discriminative method, because you discriminate between different cases. So like if you train a neural network to recognize paintings of Van Gogh, then you can feed in new paintings and you can let the trained model to decide whether this was a Van Gogh or not. However, a neural network can also be a generative method, because when we solve quantum mechanical problems with neural networks, so their neural networks are normally something which would fall under the box of discriminative methods. But when you solve differential equations, you actually generate a solution with some points, which then are given as input, so the positions of the particles. And then you keep iterating till you have found the solution. And then the neural network actually generates a solution for you. So a neural network can also be seen as a generative method. The only distinction in general, when you solve a differential equation, is that the neural network does not give you a probability distribution. So generative methods are extremely popular nowadays because these are the methods which are used to actually make images. If you look at a software like DALL-E, which probably some of you have used to generate images, this is based on diffusion methods, which are a set of generative methods. Now, a neural network, however, when you apply it to quantum mechanical problems, your solution is a wave function squared, which is a probability. So from a quantum mechanical point of view, a neural network becomes a generative method, even though in its traditional way is not perceived as a generative method, because you don't generate a probability distribution, you just fit some data. So you can use a neural network to fit a function, but the neural network does not give you a probability distribution, okay? So these are some of these kind of basic distinctions. But when we look at quantum mechanical problems, then there is not that kind of sharp distinction between neural networks and Boltzmann machines and generative methods. Okay? So what I want to do is actually to start focusing on the Boltzmann machines first. And then we will do the neural networks next week and the week thereafter. So within the next 3 weeks, you should have everything which is needed in order to solve project number 2 with neural networks. Okay, so what I want to do is actually to switch over to the whiteboard. So let's do that. So I just wanted to try to give you this kind of overview, and I'm going to repeat some of these aspects when we now look at the, let me just bring up that one. You don't need to look at my bike in the background. Okay, so the basic thing which we are going to look at now are neural networks and Boltzmann machines. and neural networks. So Boltzmann machines are, by obvious reasons, they're actually linked with the way with the Boltzmann distribution. The name should be pretty obvious when it comes to that. So what we are going to do now is that the trial wave function psi of t is now replaced by a neural network. So I'm going to use NN, and then I'm going to use a BM here, or as acronym, or BM, neural networks and or Boltzmann machines. What you're going to see now is that the basic ingredients which you had from project one, so from project one, we have the expectation value of the energy. And now I use this sloppy this sloppy physicist approach. And this is just given by the formal definition. So we have the P, the wave function. So this depends on a set of parameters, alpha. And we have the P, which now depends on some coordinates, and this alpha. And we have the local energy, which also depends on R and alpha. So I'm just setting up the equations as we have seen them in project one. So this is just the basic equation from which we start and do the Monte Carlo sampling. And what we also need is the derivative, which we also have from project one. And what we did was actually to drive this to zero. So this is the optimization part. And we have programmed these equations. And we have also programmed things like the blocking method, the bootstrap method for the statistical analysis. So these elements are the elements which we are going to use again and again. However, when you look into textbooks on the optimization part for the Boltzmann machines, that's a little bit different from what we have done in project one. So I want to first give you the standard textbook optimization part for the Boltzmann machine. But we are going to replace the gradients which you get in the standard optimization part for deep learning with Boltzmann machines with the equation for the gradient, which we had in project one. So the only thing which we will change then is actually a trial wave function, which is given by a Boltzmann probability. That's going to be the main change. And I will try to explain to you the basic ingredients which we need to set up. But let's now take a look at these Boltzmann machines and the probabilities. So these are normally called energy models. So let's look at the mathematics BMs, also known as energy models. So just to make a kind of story short, what we know with the Boltzmann machine, which you are probably very familiar with. So the Boltzmann distribution, which is the likelihood of being in a given state, I, is given by the energy, E of I, multiplied with the inverse temperature, okay? And this is then divided by the normalization constant, which is the partition function. Okay, this is a Boltzmann distribution. The way you probably have seen that in standard courses in statistical physics, statistical mechanics, etc. Okay, so this is the Boltzmann distribution. And beta is then inverse temperature with Boltzmann's constant times temperature. And Z of beta is a normalization constant. It's also called the partition function. So we are summing over all the states the system can be in. And this is actually the difficult part when you evaluate it. And for those of you who've studied the Ising model, you know that the partition function, as soon as you get beyond some few spins, becomes an intractable object. So it sounds like a kind of mission impossible here. So what we are going to do now is to replace the trial wave function. So we will let psi of t squared, this is our probability distribution, is going to be proportional with e to the minus, and I'm going to just write a function here, and we are going to put beta equal to 1 divided by z of beta. That's essentially what we are going to do, but beta is now going to be replaced by parameters theta, which are the parameters of the neural network. So we are not going to use this as a parameter, but we're actually going to use the parameters of the neural network. So we will actually train a probability distribution, which now contains the partition function. However, we know that from the equations which we had for the local energy, we are going to look at ratios between probabilities, and then we will see that the partition function actually disappears. But let's now look at the so-called Boltzmann machines, and they are normally called energy models because this E is a function which we can make as a model, okay? So what we are going to do now is simply to make this a little bit more generic. So we are going to define a set of random variables which are given by this domain here, and we are going to look at discrete stochastic events. So these x's are random variables, and this is a domain of random variables, and we are going to look at a discrete domain because at the end, even though our problem is of a continuous type, when we now approximate it on a normal computer, we always discretize. So for all practical purposes, everything we do is a discretized problem, even if it's originally is a continuous one. So this is the domain of events. And then I'm just going to define a probability distribution. And we are going to assume that these guys here are independent and identically distributed. All of these, okay? Then we are going to have a probability P of X, which is now the product of the individual probability. So these X of I's are in the domain of X. So this should be an uppercase letter. And then I have a P of X of I. This should be an uppercase probability, and this is a lowercase probability. Okay. So this would be the case if we have a harmonic oscillator, for instance. And we don't have interactions between the objects. And then we can simply set up the probability as just a product of different Gaussians. In case of a harmonic oscillator, this is exactly the wave function. So in our case, or wave function squared. So this is a general statement. And what we are going to do next is now to assume that we can find that we have a set of parameters which I'm going to call theta, which optimize the probability. And in the statistical literature, this is called maximum likelihood estimation, MLE. So obviously, we don't want to minimize the probability. Nobody's interested in zero probability. So when it comes to the probability, we want to maximize it. That sounds reasonable, right? We don't want minimum probability of finding something. So that means that what we have now is a maximization problem. When we looked at project one, we were looking at a minimization problem. So what we want then is that the probability which we have, this P of X, is now replaced, this is an uppercase P, is now replaced by a probability which depends on theta. Okay? In a sense, this is what we did with the variational Monte Carlo as well. We try to find parameters which optimize our probability, which is the wave function square. But then we actually did plug in a specific parameterization for the wave function in terms of a functional representation here. So what we're also going to introduce now is something which is called hidden variables. So this is a trick which was used long before people actually introduced machine learning concepts, and was actually called a shadow wave function. In a sense, this gives you more flexibility in the fitting, right? So we introduce a latent space or hidden space, latent variables. These are also called hidden variables. And for those of you who are familiar with neural networks, you will see that this will just correspond to the hidden layers in a neural network. So that means that what we have then is that we have a new domain of stochastic events of H0, H1, up to some H of M minus 1, like this. So these hidden variables don't need to be have the same dimensionality as the X's. So that means that the probability distribution now moves over to this P of X, which previously had theta, is now being replaced by P of X, and then we have this H and theta. So this is our probability, because we have these hidden variables. However, and now I'm going to bring up some elements from statistics, and you may have heard of something which is called the marginal probability. Does that ring a bell? So let me just define it. So we then, what we need to do is to introduce this marginal probability. So this is the quantity we want. So we want to find the wave function, for instance, as a function of the positions. And that means that we need to sum away this H of I, of H, of P, of X, and then I have my H of I, of theta. This is the marginal probability. Now, think of you as an example. Think of you having a probability which describes your likelihood of being in 2 dimensions. So according to my wife, I live in only 1 dimension. So in a certain sense, if you think of H as the Y position and X as the X position, what you would do then is to sum away the Y position, and then you find the probability of being in X given all the Y values. So if you want to extrapolate from what my wife says, I mean, I'm a person who's a marginal probability. Okay. And my daughter always agrees with my wife. Yes. Don't take me too seriously here. But this is the marginal probability, right? Because we want these degrees of freedom X, right? Now, if you have a continuous variables, this sum is replaced by an integral. But we will always deal with the continuous variables. So what we are going to have then is an optimization problem. And that optimization problem is now you finding the optimal, which is then given by argmax of all these theta values, which now are assumed to be real variables. They could be complex if you want to. And then we have the function P of X of theta. And in principle, this P of X, just to remind you of that one, of theta, if we now just look at the variables x, where we have assumed that the x's are independent and identically distributed, this is now given by x equal to x of I as a function of this theta. Now, we know that this problem here, if you look at that one of the problems we face now is that if we want to optimize in the optimization part, what we want then is the gradient of P of X of theta equal to 0. That's the optimization part. Now, when you look at the function which we have a product, and that is often a little bit more complicated. Unless your function P for the individual probabilities X of I is a simple function, then this can become pretty awkward from a mathematical point of view and a computational point of view. But there is an equivalent problem here, which simplifies life. So instead of optimizing the product, is there another problem which we could actually look at? So think of now optimization, maximization means that we need a concave function. And there is one function which is always concave. No, the log. The log of P. That is an equivalent problem because then in the optimization, we know that the log is a concave. If you don't like maximization, you can minimize. And then you can just put a minus sign in front of the log because then the log is a convex function. So taking the log here actually simplifies this because then instead of a product to take the derivative of, we simply have a sum. And then we have the individual probabilities. So if you think of this P of X as being exponentials like the harmonic oscillator, then you would have e to the minus x squared times some constants. And if you take the log of that one, this is just x squared, right? So the expressions become very simple. And you will see that when we're going to implement it in the calculations, when we plug in this explicit Boltzmann machine, we're actually going to take the logs. And that simplifies many of the calculations. So what the equivalent problem, equivalently, is now that the function to optimize. So keep in mind now that P here is the probability. And this defines, for those of you familiar with machine learning, the cost or loss function. But at the end, you will see that life becomes much, much simpler if we optimize the energy, like we did in project 1. So what I'm doing now is to give you the standard path for Boltzmann machines where you optimize the probability. But this gives to us equations which are less easy to implement efficiently than taking the energy as a cost function, which we had in project 1. So in machine learning, you always have a function you optimize. And that could be the mean squared error, if you're fitting a polynomial, for instance. It could be something which is called the cross entropy, or the function which is best suited for your problem, which in our case here is a probability or the energy. So the equivalent problem, which we would face then, is that this theta is given by argmax. And then I just write theta and assume these are real variables. And then I would take log of P of X of theta, which then is the same as argmax of theta. And then I simply have a sum over all the i's here, x, and then I have a log over the P of xi of theta. So hopefully you see that this is an uppercase P, which is the product. And here we have just the sum over all the xi's. Or if you like a minimization, or theta is argmin, and we know that the negative log is, let me just correct that one. This is a convex function of I of log of P of xi of theta. So this is a standard way. This is normally done with Boltzmann machines. Now, what I'm going to do now is actually to set up an example of a Boltzmann machine. And this goes back to the paper by Carleo and Troyer and how they actually implemented the Boltzmann machines in the first round. So let's now look at the Boltzmann distribution. So what we are going to do now, since we have this probability, which depends on this variable xi and some hj, the hidden variable, this is the full probability. But we are going to sum away the h's at the end. But this is where we start. And this is now given by some function, which I'm going to call f, x of I, h of j, of theta, divided by the partition function, which is now a function of theta. So this is a normalization constant. So z of theta is now simply xi, the sum of all the xi's and all the xj's of f of xi hj of theta. So think back to the standard Boltzmann distribution. If you look at the standard Boltzmann distribution, you have the probability of being in a state I, which is e to the minus beta e of I, divided by z of beta. And z of beta, which is the partition function, just to remind you of what we wrote up earlier, it's the sum of all the energies beta e of I. Okay? And now what you see here, if you want to link things, you see now that this function f, which we have here, is the same as the exponential here. And the partition function here, with a function of, as a function of beta, is the same as this partition function here, or normalization constant. Okay? That sound, this is just to make up the kind of parallels which you have here. Now, what we are going to look at now is a simple example first. So we are going to assume that, and this is the standard approach which we're going to take, and I'm going to skip this subscript x I h j. So I'm just going to write x h of theta. We are going to assume that this is something which we can rewrite now as an e to the minus a function e, which is a function of x, h, and theta. So it's a lookalike of the standard Boltzmann distribution, okay? And this is the Boltzmann machine, essentially. So we could now make a model for this e of x of h of theta. And the simplest case, so this is where you make the model. So in the Jupyter notebook for this week, you will see a specific model for this function e. And that will define your trial wave function. Because remember now that this quantity here is going to be proportional to psi t squared. Okay? So we are making a model for the wave function without knowing anything about the wave function. Okay? So the very simplest case is something which is called a binary-binary Boltzmann machine, BM. And it has an R here. And R stands for restricted. So this is restricted. So what we make then, when we say a binary-binary, it means that every value x takes only two values, 0 or 1. Okay? And hj takes the same value, 0 and 1. Okay? That's pretty straightforward. And now I can make a model. So my model for this function E of x, of h, of theta is going to be equal to a sum from I equals 0 up to n minus 1. And then I have some xi, which can be either 0, 1, and ai, which is a parameter, plus a sum over the hidden nodes of m minus 1 of hj times bj, plus a sum over ij, and this goes up to n minus 1 of m minus 1. And then I have xi multiplied with wij multiplied with hj. So if you look at this now and think back to, this applies to those of you who have studied the Ising model, you could now replace x and h with spins. And then you will see that the last term is just the interaction between two spins. The two first terms are the sums over the individual spins, multiplied with some constant. But when we now translate this into a machine learning language, these h's are going to be the hidden layer. The x's are going to be the input layer. The a and the b's are going to be the so-called biases, which we have in machine learning. And the w's are going to be the weights. So in principle, the w's are actually the interactions between the hidden layer and the visible layer, the input layer. You could think of the spins. So this is actually, what you have here is a lookalike, a more generic form of the standard Ising model. You see the connections? So what I can do now is to set up a neural network, or Boltzmann machine, as it's called. It's actually a neural network, where I have the following. So my parameters theta, so I can actually rewrite this equation here as a vector A times a vector x plus a vector B, which are the biases, times H plus X transpose times a matrix W times a vector H. And the parameters theta then are actually given by these vectors H and B and the weight matrix. So to give you a simple example, if n is equal to 2, then I have the following options for the x's. So let me just do this and then we take a break. So I can, if I have two x values, they can be 0, 0. They can be 0, 1. They can be 1, 0. And they can be 1, 1. And I'm also going to assume now that m for the hidden layers is equal to 2, and then I have the same possibilities. What I can do now is to set up a network where I have x0 and x1, x1. And then I have my hidden nodes, h0 and h1. Now, these are connected. So here I would have a connection, w00, which is a parameter I need to find in the optimization. This will be 0, 1. These are connected by 1, 0. And finally, we have the last one, which is w11. And here we would have a parameter b1. These are often introduced in order to avoid that by accident, the training stops because the weights are 0. Here I have a parameter b0, a0, and a1. So in total, I have 8 parameters to fit. So you could think of the x's as your input variables, the positions of the particles, or the spin values. If you think of the Ising model, you could arrange your system now with the spins being pointing down, which is 0. So that's a possibility. And this layer, which you see here, now we're going to take a small break. This is called the visible layer, because these are the parameters you're interested in. This one here is normally called the hidden layer. It's called either the visible or the input layer. Now, you can obviously have more hidden layers. So you can keep stacking here, but by experience, what has happened is that, or what people observe, is that the training becomes more complicated. So a restricted Boltzmann machine means simply that you have one hidden layer. That's why you have the name restricted. But you see that you can obviously stack this and have more and more hidden layers. That gives you a more complex object to train. The other thing is that in the Boltzmann machine, in its original form, also included interactions between the nodes in the visible layer. So we call typically these nodes or neurons. And it also had connections between the nodes in each layer, hidden layer. That again makes the training much more complicated. So the kind of function we end up with is a function like this one, which you have on top here, which is a lookalike of actually the Ising model if you replace x and h with spin values. So if you look at that case you have there, that is actually a two-dimensional lattice for the Ising model. But where we are going to integrate away, or sum away, one of the degrees of freedom, because at the end, we want a probability which only depends on the x's. Because these are going to represent the positions of the particles. So if you have a system with 10 particles in 2 dimensions, you need 20 input nodes. Does that make sense? 10 particles in 2 dimensions, you need the x and y's for everyone. So then you need 10 times 2, the dimensionality, 20 input nodes. And you can obviously have as few or as many nodes you need here. But just keep in mind that, and this is a problem, I'm going a little bit over time here. Maybe we should take a stop, okay? Let's take a break of 15 minutes. So before the break, we looked at what we call a binary Boltzmann machine. And in this particular case, if you wish to interpret these x's and h's like spins, you see a close link with something like the Ising model. Now, there's one small problem I wanted to mention here. So if you think back, for those of you familiar with the Ising model, you see now that the number of so-called configurations. So for the x's, you see here that you can have 4 possibilities. So x can be 0, 0, or it can be 0, 1, or it can be 1, 1. And the same applies to the h's. So we call this a configuration for x and a configuration for h. In this case, we have 4. So that means that if you now go back to the ugly beast, this is actually the problem. The root of all evil is the calculation of the partition function. Because you see now that if we sum over configurations here, the possible realizations, then we would have here, when we look at the sum, in this case, we have just 4 and 4. So that's just 16 possibilities. So that's something which we can easily calculate. However, so in principle, if you now look at the configurations you have, this is just 2 to the power of n. And here it will be 2 to the power of n. This is a binary problem. If I replace this with 20, then I would have 2 to the power of 20, which is the same as 10 to the 7. So if you go back here, then I would have 10 to the 7 squared. And this is something you just say bye-bye. You give up. even for such a small case. So if you have 10 particles in 2 dimensions, you need 20 input nodes for the binary case. So this is one of the basic problems which you have in statistical physics to calculate the partition function. And for those of you who have taken a course in statistical physics, you know that when you have the partition function, you can actually derive all thermodynamical relations from that. Whether this is the grand canonical, the pressure canonical, etc., you can actually obtain all the thermodynamical quantities of relevance. Helmholtz free energy, Gibbs free energy. You can evaluate the Maxwell relations for derivatives, etc., from the partition function. So in a certain sense, you can also hear that statistical mechanics is one of my favorite topics. It was since I was a student. You actually can do thermodynamics from microscopic physics. And that's actually a fantastic starting point. And but in our case, you will see now that what we are going to do now is what is called the traditional Boltzmann machine approach, which we will not use. But I'm deriving that to show you how you can do it, how you can do the optimization. So when we are now doing the optimization, if we look at the basic problem which we have in the optimization, so let's bring that back, and then you will see where the problem arises. So the optimization, that means that we are taking the derivative of log of p of x of theta, and we want that one to be 0. Now, what we need then is, when we now look at it, when we write it out, this is the same as us taking the derivative of the sum over all the xi's of log, and now I'm plugging in. So before you write this one, let me just bring back the expression which we have. So I'm now using this expression here, okay? But I'm suppressing the summation over the h's. So what we have then is f, we have to bring in the h's afterwards. So we would have this function here, that is one of the derivatives, minus the derivative of log of z theta. So this is a gradient, which we want to drive to 0. Now, for the first term, we do actually have a function dependence. So we have a function which we made in the model. So when I make this model for the Boltzmann machine, then I have a model which I can plug in the first term. And then I just need to take the sum over the logs and take the derivatives. And if I have assumed that this function here, suppose that this function which you have here is an exponential of something, minus e here, then when we take the log, that means that you just need to take the derivative with respect to this e to the minus e here, which will depend on the parameters and theta, etc. So that makes life much simpler. So if you think of this as just harmonic oscillators, then you just get x squared times some constants. And that's something which is easy to calculate the derivative of, right? So the first term is normally not problematic. It's the second term, which in the traditional picture is actually bringing us into problems. And you have to make some you have to find some ways to evaluate it. So let's look at that one. So what I'm doing now is to present to you something which we're not going to use. So it's not a very pedagogical thing, but because we are not going to optimize the probability as a cost function, but we are going to optimize the energy with a Boltzmann machine as an ansatz for the wave function. So let's now look at the theta of log of z of theta. And we know this is actually the same as the derivative of z of theta divided by z of theta. Okay? So let's keep this with just x. But keep in mind that when you look at this expression here, there is a missing summation over the hj's, the hidden layers. But I'm just going to suppress that. That has to be taken into account when you're setting up actual calculations. But let's now look at how we can evaluate this second term. So this term which we put up of z of theta, and this is actually the difficult one, this is the same as the summation over xi's in the domain of stochastic events of f of xi with respect to theta divided by z of theta. So the function which we have, the z of theta, is now a function. So if you now look at the function z of theta, this is just to remind you of that one. It has a sum over xi, it has a sum over hj, and it contains f of xi hj of theta. But in the equation here, just to reduce notational clutter, I've actually suppressed the sum over hj, okay? And that's why you see it only as a function of x here. But when you evaluate it, you actually have to include hj. Okay? So this is just a kind of more compact notation. So if you look at the expression which we have then, when we take the derivatives, then we have now, if we now also use the fact that xi of theta is the same as the exponential of log of f of xi of theta. So we can always write it like this. Now, in our case, we know that this f is normally given by an exponential with a function as an argument. If you think of the Boltzmann distribution. So that means that I can actually rewrite this function here of z of theta as a function of where we have a sum over xi's, and then I have del theta, and then I have the exponential, and I have the log, and now I'm just writing f. Again, to reduce a little bit the notational clutter here. So here I'm just using this expression, and I plug that one in here. If I do that, what I get then, so let's just wait a little bit so people have time to write. And in the meantime, you can admire my ugly handwriting. So if we do that, what we will get is a sum over xi, and then I have the exponential of log f, and this is multiplied with the derivative with respect to theta of log f divided by z of theta. Now, what we have here is nothing but xi of f of xi of theta multiplied with the log of fxi, and at the end we have to introduce the summation over the h's as well, divided by z of theta. Now, if we now look at this term here, this is nothing but the probability. So this term which you see, now let's just mark it, this term here is actually the probability of p of xi of theta. That's just a definition which we have. So what we get then is the following expression. So we have xi, and then I have the probability of p of xi of theta multiplied with log of fxi of theta. And this is nothing but an expectation value. So this is the same as the expectation value, because we have a probability times a function. So this is nothing but the expectation value where xi lives in this domain of the quantity log of f of xi of theta. Okay. And I have suppressed here h. So there should actually be an expectation value with respect to the stochastic variables x and the stochastic variables h. So I have suppressed the h degrees of freedom, but they are there. This is something we can evaluate by Monte Carlo calculations. So what it means then is that the optimization problem, if we now rephrase it, or summarize it, so the cost or loss function is now the probability P of xi of hj of theta. That's the loss function which we are setting up, which is then given by a function where we make a model xi of hj of theta divided by z of theta, the normalization constant. And we should ring in here this function here, which is our model. And that obviously enters in here as well, because that is the way we use the model to define the normalization constant. And then the optimization of del theta of P of x, h, and theta is then given by this summation here, where we would have the first term, which was pretty straightforward to evaluate, which is just given by the sum over the, so I would have a del theta, and then I have log of f of x of h and theta. This is the first term. So I'm skipping the summations now. I'm just setting up this in terms of vectors x and h minus the expectation value. And here I have x following the domain uppercase letter x. And then I have h, which follows the domain h. And this is an expectation value of the derivative of log of f of x of h of theta. This is the typical way you optimize a Boltzmann machine if you want to use a Boltzmann machine to generate new images. So you could have as a training data a set of images. And then this could be numbers, handwritten numbers from 0 to 9, which is the famous MNIST data set. Then you make a model, which is represented by this function f. And with that model, you can then start training a probability distribution. And when you have trained the probability distribution, you found the parameters theta, then you can use this P to generate new images. And Boltzmann machines actually, before people started to use CNNs, convolutional neural networks, for image recognition, Boltzmann machines was actually one of the viable approaches to image recognition. But then CNNs became much, much more effective. And with huge trained data set like AlexNet or other ones, that has in a way, how to say, what do you call it in English? I mean, it has knocked out the interest in Boltzmann machines in the machine learning community. But then for quantum mechanical systems, there's been a revival, but we are not going to use this optimization problem, but we're going to optimize the energy, because that's where you have the Hamiltonian, which drives the system to its minimum. So we are going to, in our case, in project 2, the first starting point. So does this sound okay? So this is called a contrastive divergence. So you get the optimization, which contains two terms. And this term, which you see here, is evaluated by Monte Carlo sampling. That's the standard approach which you use to sample. Okay? Now, what we will do in project 2, the Boltzmann machine part, BM part, that is to optimize the energy. So we are going to take the energy as a cost function, is the expectation value of the energy. It's actually the local energy as a function of these parameters theta. So previously we called them alpha, because you had a parameter alpha in the trial wave function. And then we are going to evaluate the same derivatives as we had before of the expectation value of the energy. But now the trial wave function is going to be given by a Boltzmann machine. And we can choose whether we want to have the trial wave function or the trial wave function squared. When we use the logs, we just get a factor of log 2. But we are going to approximate this one with a Boltzmann machine. And in that case, we are going to have a function which will depend on x and theta divided by the normalization factor theta. And where this f of x of theta is actually a function which has a sum of all the h's, and this contains an f of x of h of theta. So what we are going to look at now are different ways of setting this up, okay? So when you take this approach, you see that there is not much new which you need to program. So the thing you need to program is actually the new trial wave function, where this f is going to be given, in our case, by different types of Boltzmann machines. So the way you can think of this now is that we can have f of x of h of theta. So there are typical Boltzmann machines. One is the binary, and we use a restricted Boltzmann machine, binary RBM. So we are not stacking more than just one hidden layer. We are not going to have connections between the nodes in the same layer, and that's why we call this a restricted one. You will see that if we do that, we are not going to get a very good results, because the input then will be just binaries. This would fit if you have a spin model, where you can have spin up and spin down, and that means that you have a binary input. But when you look at a continuous case like we had in project 1 with the harmonic oscillator, we need to change that so that the input could be continuous, but the hidden layers could be discrete, okay? So what we would have then would be, so that could be one option. So let's call that 1. But then we can have 2. So this is, when I'm setting this up, I'm thinking of input and hidden, or visible and hidden. But we can have a Gaussian binary, RBM. We could continue along these lines. So we could have a Gaussian, so we could let the hidden nodes be continuous. Gaussian, RBM. And you see that there is a lot of flexibility here. Now, in the code example you will find online, we are going to implement a Gaussian binary. That is something which gives us a simpler wave function, trial wave function. And since we have a harmonic oscillator which doesn't interact in the first case, then a Gaussian is pretty close to a harmonic oscillator. So that means that we have a Boltzmann machine which already has some of the basic components of the harmonic oscillator. However, when we add an interaction, then the Gaussian binary Boltzmann machine does not have enough expressivity to take into account the correlations between the particles. And you will see that the energy then is not very good, which you get with the Boltzmann machine. So the reason why I bring this up is, one, it's these Boltzmann machines. One, it's pretty straightforward to implement in project number 2 from project 1. But you will also realize then that the Boltzmann machines have less flexibility if you're dealing with continuous variables. So that means that you would have to change the way this function f of x looks like. Okay? So that's the overarching thing. Sounds clear? So that's the reason why we later are going to look at neural networks, which actually give us much more flexibility. Okay, so let's, but the reason why we bring it up is because this was actually where the field took off from. So when Carleo and Troyer introduced this paper and applied it to the Ising model, and this is actually something which you can think of as a variant of project 2. If you didn't like so much the harmonic oscillator case, and you would like to study the quantum mechanical Ising model, then actually this binary model and reproducing what Carleo and Troyer did could be a very viable path for the second project. Okay, just give it a thought, and we can discuss these things after the break. Okay, so what I'm going to do now is to switch over to the whiteboard, and I will show you the expressions which need to be coded. So let's just do that. And oh, sorry. So in here, in the beginning, what you will find is a lot of the same stuff which we discussed in the on the whiteboard. And the first part of these of this Jupyter notebook follows what we call the traditional optimization path of a Boltzmann machine, where we optimize the probability and then find this so-called contrastive difference between the when we take the derivative of the probability. So the first part is something which you can happily jump over, but it more represents a kind of background. So this is typically the distributions which we have. So let me just increase a little bit here. So this is a standard Boltzmann machine, and typically you set the inverse temperature to just 1, and you just leave it out because it's just a constant which doesn't play any role here. So the typical Boltzmann machines would be the binary, which we have discussed. And then we have so these are the energy functions, right? Which then enter into this definition. And here I have suppressed the parameters because the parameters are then given by the so-called biases, which you see here, and the weights. So this is a binary Boltzmann machine. And here we have the Gaussian binary. And this is the one which I have implemented in the code which follows at the end of the lecture notes. So in this specific case, what we have now, you see, this is something which could be suitable for a harmonic oscillator, because you would have the exponential of e to the minus this one. And then you know that the harmonic oscillator has an analytical solution which is proportional to this x. This a becomes a parameter. H is obviously the hidden node, which takes value 0, 1. And B is then just the role of a parameter, plays a role of a parameter, which we call the bias. And then we have to find the weights here. But often you would just set the sigma to 1 if you don't know how to set up the value for the standard deviation and the variance. So it's pretty common just to put this was to 1. So this type of Boltzmann machine is useful when you model continuous data, which is the case when we now look at the positions of a particle and we want to model, let's say, a many-body system with the positions of the different particles, because then the x's are continuous variables. So this case which you see here is just a repeat of what I did on the whiteboard. So we can just neglect this one. And you see again, you have the optimization part, you have the derivative of this function, which we put up, and then we have the derivative of the log of z. So, and as a function of the different parameters. So this is often called the data set, and this is just the model one. They often have names, and we went through these derivations here. So we are just going, I'm going to skip these, and you can see that typically if you have the binary Boltzmann machine, you would have some simpler expressions for these derivatives. And it's actually not so difficult to see how these derivatives are going to look like. Okay? So there are things here which we are not going to need. The thing which you will also need in case you want to optimize the probabilities. So these are the probabilities which we also discussed on the whiteboards. Then when we have these different Boltzmann machines here, you can actually find expressions for the different probabilities. But as I said, so for the binary Boltzmann machine, this is what it's going to look like. If you have a minus, if you take away the minus sign, it's going to look like that. If you have the minus sign, it will have a minus. And this is the partition function which you're setting up. And when you then want the probabilities over the x only, then you would have to sum over h. So this will give you the marginal probability. And for the binary Boltzmann machine, this ends up being given by this expression here. So one of the reasons why these Boltzmann machines were very popular, this type of Boltzmann machines like binary, Gaussian binaries, is that you could actually calculate these different probabilities because you need to know what is the probability of finding x and the probability of finding h when you're setting up the algorithm for optimizing the probability. As I said, all these details which you see in the slides, they pertain to the case where you just want to optimize the probability, okay? Which we will not do. So there's a lot of background information, but I kept this background information because this is useful in case you would like to program a Boltzmann machine for fitting something else than a quantum mechanical problem. Okay? So you also have the conditional probabilities because we use something which is called Bayes' theorem in order to set up different probabilities. And typically when the node fires, so we have the probability which HA equal to 1 given a value of x. And this is something we can also calculate analytically. And these are equations which we would have to program if we optimize the probability. And what follows then is also almost a sadomasochistic exercise with a Gaussian binary. You can do Gaussian, etc., etc. So you get just more and more complicated expressions. But this is not what we will do. So this is just added, not to intimidate you, but as for the sake of completeness, and in case you wanted to optimize the probability. But what we are going to do now is to define something which we call a neural quantum state. So that means that our Boltzmann machine, which is given by the model which we have, this x h divided by the partition function, we are going to replace the wave function with that. So we could choose either that the wave function is given by the Boltzmann machine itself, like that, and then you will get a specific expression where it looks like this when you have a Gaussian binary. So this is the expression you get. Alternatively, which is more correct, is actually to set up the Boltzmann machine like that. So in our case, we are going to deal with a real wave function. So if you have a complex wave function, you have to be a little bit more careful. Because for the harmonic oscillator case, the wave function is going to be given by real parameters. Okay? So what you can do then is simply to set up, say that the wave function is equal to the Boltzmann machine. So this is your trial wave function now. The only difference from project one is that the parameters now are given by the parameters of a Boltzmann machine. So you have defined a neural network, which is given by a hidden layer and a visible layer. And then you have the parameters, which are the biases and the weights. So this is pretty close to what we did before, except that now we have made a specific model. And you will see that this model here, for the non-interacting case, is going to give us basically the exact result. But as soon as we add an interaction, it will not, because it doesn't have enough information about the physics of the interaction. So this is the wave function. When you do the math here, I get the final expressions, which are just given by this term here. So this is the equations which we have to plug in when we now are setting up the optimization problem. And then the cost function, in our case, is just going to be given by the one which we have seen before. So previously, we had the parameters alpha, but now the parameters alpha, in order to link this with what we did before, we see that the parameters alpha are given by these biases and the weights. And then you remember that what we did in project one is that when we had the derivative of the wave function, in order to calculate these specific integrals, we needed the derivative of the wave function. So this is the gradient, which we programmed in project one. And then you see now that what we have is the log here, which has an expression which is a little bit simpler. We're normally going to put the sigma to 1. We have the derivatives with respect to the parameters A, the parameters beta. So these are the derivatives which we need to set up. So when we, in project one, we had a very simple trial wave function which depended only on one parameter alpha. What we did then was to find the derivatives with respect to alpha, which is actually something which looks like this. This is what you had in project one, but now we need the derivatives with respect to the hidden layers. So these are parameters we want to optimize. So this will be the set of derivatives which we need to set up now. And you see now that if suppose we have two particles in 2 dimensions, then we have 4 input nodes. So that means that there would be 4 values of A. And if we then have 2 hidden nodes, there would be 2 values of B. And there would be 4 times 2, 8 values of W. So in project one, we had just one derivative because we had one parameter alpha. But now with the 2 particles in 2 dimensions and 2 hidden nodes, we would get 4 derivatives for the first one, 2 derivatives for the last one, and 8 for that one. So that means that we have more integrals to evaluate when we do the Monte Carlo calculation and the optimization. Because in project one, we simply had one such gradient, right? But now we need more gradients. If we then, instead of, and you see the direct link with a neural network, instead of having a Boltzmann machine like this, we could replace all these with neural networks and hidden layers. Then you would obviously have more parameters. So when we start with a neural network, you could typically have something. So a neural network would then be, and let me, no, maybe we take that next time. But these are essentially the derivatives you need to plug in. And I put up the explicit expressions here. And these are the expressions which are being programmed. And in this particular case, it's the electron case. So let me just sneak in 5 more minutes because I wanted to show you the code which we have here. So this is just the manipulations of the local energies, etc., and the derivatives. And at the end here, what you have now is a trial wave function, which is given by this Boltzmann machine. And you can see now that I look over the particles, I have the number of hidden layers. So this is a Gaussian for the input, the visible layer. It is a binary for the hidden layers. So this is the total wave function, which has the input layer and the hidden layer. I calculate the local energy here. I set up, in this case, I have analytical expressions. I do the calculations with and without an interaction put on. This is a case for 2 electrons in 2 dimensions. And you see now that the only thing which changes from the previous codes is actually the expressions for the wave function, the expressions for the local energy, and the expression for the derivative ansatz. Then I have the quantum force, which I also have to calculate for those specific wave functions. So I'm using the analytical expressions here. And then I do the energy minimization, as you can see here. And if you just scroll down, what you will see at the very end here is that I have assumed now that I have 2 particles, 2 dimensions, and I have only 2 hidden nodes. So if I now take the let's just run this calculation. And then we are going to bring this back again next week and discuss it further. So this has a plane, you can see now a plane gradient descent where I set up the energy derivatives using exactly what we had in project 1. But now the derivatives will depend on the functions of the variables A, B, and W. I'm going to have the gradients for all these quantities, and these are obviously vectors. And then I'm updating them with a learning rate. And what you will see now for the non-interacting case, which is this one, for the non-interacting case with 2 electrons in 2 dimensions, the energy is 1 for 1 electron with the harmonic oscillator frequency to 1. So it's 1 plus 1, it should be 2. And you see now when I do these iterations back and forth, I am roughly getting, since I have a harmonic oscillator lookalike in the Gaussian, you see now that the energy is fluctuating around 2. Okay, so I had some problems. What did it say here? Okay, let me rerun this now by setting the interaction true. So now I'm adding the Coulomb interaction for the 2 electrons. And the exact analytical result, this is a case where we have analytical result for 2 electrons with a harmonic oscillator frequency equal to 1, scaled in atomic units. That should be equal to 3 atomic units. That's the exact result. And you may remember when I showed you this case with the variational Monte Carlo calculation, where I had this Jastrow factor, I was almost spot on 3. But now I don't have this Jastrow factor. If I now run the calculations again, so let's do that here, then you will see that the energy is not going to be free. It's actually going to fluctuate a lot. But the best one I'm going to get is roughly 3.2. And that is simply because my Gaussian binary Boltzmann machine is not good enough. So what you could do then is to take the Gaussian binary part for the single particle piece and multiply that with a Jastrow factor. Then you will get close to 3. If you, however, when you look at neural networks, if you do that, you will often get a result which is much, much closer to the exact result. But I was thinking that the Boltzmann machine could be the starting point, especially since not everybody's familiar with neural networks and machine learning, because then you have a pretty, direct implementation of the wave function in terms of a Boltzmann machine. And for the harmonic oscillator, you will see that you're going to be basically spot on when you have a non-interacting system. So we will continue next week and the week thereafter with the discussions on how to implement these equations. We will start again with this one next week and look back at the equations, but take a look at the equations at the end of the slides. The intermediate part is only if you optimize the probability, which we will not do. But that is the standard way you implement a Boltzmann machine. Okay? So let's take a break. And then we can use the time now to discuss options for the second project.